All right, here's another example. We're once again going to do the same analysis. We're going to analyze the cations first, then look at the products, figure out the kinetic product and the thermodynamic product. The cation analysis is a little bit harder this time around, so let's jump right in. All right, so again, we have carbons 1, 2, 3, and 4 that are part of our conjugated system, right? We have a double bond between 1 and 2, a double bond between 3 and 4. We're going to add H plus to either carbon 1 or carbon 4 in order to make a cation at carbon 2 or carbon 3. So what happens if we add a hydrogen to carbon 1? We make a secondary cation here that is resonance stabilized. Or we can add the hydrogen to carbon 4, which gives us a secondary cation that is resonance stabilized. Now, you'll notice, of course, that both of those were secondary cations. Secondary cation and a secondary cation. So at first glance, we may think, well, we're kind of stuck here. We don't really have a difference between these two cations as far as stability goes. But notice how the resonance works out. If we draw the resonance structure for each of these, we can move this pi bond over to distribute that positive charge, and we end up with a primary cation here. But if we do that with the other one, we end up with a tertiary cation, which is clearly going to be the most stable option. So where's our most stable cation? It's this one right here. Now this is a little bit more tricky than our previous example because it's not the initial cation that we would think, right? We have to break the double bond, make the cation, and then also think about the resonance structure to make it tertiary. But we can notice that when we look at carbons 1, 2, 3, and 4, clearly carbon 1 is the tertiary carbon, and that's where we're going to want to put our carbocation. But we know that we need to make our initial cation at 2 or 3 in order to have resonance. And so what we want to think about is how can we make a cation at carbon 2 or 3 such that the resonance form puts that positive charge on the tertiary carbocation. So this is our most stable carbocation intermediate. This is the one that will lead to our kinetic product. Most stable cation leads to kinetic product, right? Which is always the case. So we can draw the kinetic product right now. Cl minus, oh, okay. So we went and got H plus, broke the HCl bond, made the cation, drew the resonance form. Cl minus comes in and attacks that tertiary carbocation to give us our kinetic product, which is this one right here. Notice that this is the 1,4 addition product in this case, right? The hydrogen is added to carbon 4 and the chlorine is added to carbon 1. Now, the thermodynamic product is going to be the result of the other resonance structure. Well, we've already drawn the other resonance structure, so we can really quickly draw, this is our kinetic product. We've already drawn the other resonance structure, so we can have our Cl minus just come in and attack that, and without doing too much extra work, we have got ourselves a thermodynamic product. Oops, H3. This is the 1,2 addition product because the hydrogen is added to, well, it's carbon 4 and carbon 3, but if we number it the other direction, we've added to carbon 1 and carbon, so hydrogen added to carbon 1, chlorine added to carbon 2. This is 1,2 addition. And in this case, this is the thermodynamic product. And we can confirm that if we look at the double bond is tri-substituted in the 1,2 addition, it's di-substituted in the 1,4 addition. The double bond is more stable in this case, and that makes it the thermodynamic product. All right, I want to draw your attention to something, but I also want you to forget about it as soon as I say it, right? So compare the results that we got in the two reactions that we just did, right? When we did this one, the 1,2 addition was the kinetic product. When we did our second example, the 1,2 addition is the thermodynamic product. The previous example, the 1,4 addition, was the thermodynamic product. In the example we just finished, the 1,4 addition is the kinetic product. These things have nothing to do with each other. Please remember that, right? Kinetic products come from the most stable intermediate. That's all, right? A kinetic product can be a 1,2 addition. It can be a 1,4 addition. They are not, one does not tell you the other, right? If I say do a 1,2 addition, it doesn't tell you if it's kinetic or thermodynamic. You have to do the analysis of the carbocations or the products to figure that out, right? 1,4 addition can give you a kinetic product in some cases, or it can give you the thermodynamic product in other cases, right? We have to do this analysis in order to figure that stuff out. So kinetic and kinetic products, thermodynamic products come from the analysis that we just did. What is the most stable product? That's your thermodynamic product. Which product goes through the most stable intermediate? That's your kinetic product, right? That's the only way that those two things are determined, right? So we have kind of parallel classifications of reactions. We have kinetic and thermodynamic, and we also have 1, 2, and 1, 4, but the two classifications have nothing to do with each other, as we've seen, hopefully, by looking at these two examples, right? Sometimes 1, 2 is the thermodynamic product, as in this example, and if we go back to the previous example, if it will let me, sometimes 1, 2 addition is the kinetic product. So please keep that in mind, that those two things are not determining each other, right? They are separate classifications. All right, so those are examples of 1, 2, and 1, 4 additions. Those are examples of kinetic and thermodynamic control, right? If I gave you this reaction, this last reaction that we just did, and said, I'm running this reaction at 50 degrees Celsius, you would look at that and say 50 degrees Celsius is a warmer temperature, that's a high temperature favors thermodynamic. I would expect this to go through the 1, 2 addition reaction and give me this product. That's how it goes. So once you associate temperature and thermodynamic kinetic, then you just have to do the mechanism, do the analysis to figure it out from there. There are some practice sheets and such on D2L. Please check those out and practice this kind of thing. This is one of those things that after you do it a couple times, you start to kind of see how the resonance structures work themselves out. You'll be able to tell quickly which one is kinetic, which one is thermodynamic, without having to explicitly draw out the cations that don't contribute to the overall reaction. So I highly recommend practice, as always, and I hope that the practice sheets are helpful.